Welcome back. We're in the middle of the proof of Schauder's theorem. That's the statement about given a compact linear transformation T between two Banach spaces X and Y, then that's going to happen precisely if the dual transformation, that's the guy from the dual of Y to the dual of X, is also compact. At this point we have proven one direction, namely compactness of T implies compactness of the dual transformation. Now we have to do the other direction. In turn, once this is done, Schauder's theorem here is actually part of a larger theorem. We will have our first set of properties for compact linear transformations. All right, so let's do the rest. So for the converse statement, let the dual transformation be compact. Y star X star. Then by the just proven part, the dual transformation of that guy, sort of the double dual transformation, would be compact from the bidual of X to the bidual of Y. Now here, please remember, unlike the adjoint, the dual transformation of the dual transformation is not the initial transformation in general, okay? So, but now, how do we get back to from the biduals to the original spaces? Well, of course, there we use the canonical map as usual. All right, so using the canonical map, J, this is always the same thing whenever you want to go from the bidual to the original space or vice versa. You always use the canonical map. So here we haven't used it now in a while. So this is this guy. We have, so first thing to notice here is the canonical transformation is a bounded linear transformation, all right? This doesn't need that you're working on a Banach space. This works for any normed linear space. So in particular, if I look at this composition, then I have something compact on the left and something bounded on the right, and we just showed one of the earlier properties in this theorem that this thing is going to be a compact map. And here, if you think carefully, it's going to be a compact linear transformation between X and the bidual of Y. Excellent. This was the third part of this current theorem. However, if we now let capital K, right, I have only one capital J. J here is the canonical map on X. Now I will use the canonical map on Y, and I will call that guy capital K. This is the other canonical map. So Y to K sub Y denotes the canonical map on Y. And then, well, here's some curious algebraic identity. Then for any f in the dual of Y and any point x in X, I have to do a little computation. The dual transformation of the dual transformation of T. So that's gonna be a thing in the bidual of Y. So no, in the bidual of X, right? It takes input from the bidual of Y. Oh no, that's correct. What I first said is correct. So it takes input from the bidual of X and spits out something in the bidual of Y. That's correct. So in particular, it knows what to do if I stick in the image of the canonical map, right? Because this is in the bidual. And this guy here takes the bidual of X and sends it to the bidual of Y. So I can indeed evaluate it on a linear functional that acts on Y, right? this is well defined what's written here, all right? Now we just use the definitions. So this is that capital J on X is the evaluation map, J sub X, which is pointwise evaluation of a linear functional at the point X. And now we're just going to use the, that's exactly what I just said. So pointwise evaluation. Oh no, I think this direction is not the pointwise evaluation. This is the definition of the dual transformation. Dual trafo definition. The pointwise evaluation comes in a few moments. Jx t of f. So you have this, and now you use the definition of the j sub x. So this is ttf of x, and now you use again the definition of the dual transformation ft of x. Right. So dual transformation is used here. and previously, and this guy here is j of x, f is pointwise evaluation, f of x. All right, good. Now, so this is one half of the picture. Likewise, if you do this now with the capital T thing, so capital T is the canonical map on the y space. So it takes an element t of x, which is in y, and it sends it to an element in the bidual of y. So this thing knows how to act on, again, linear functional on y. Okay, so this is well defined. And now just use the definition. This is little k t of x f. And then this k is also pointwise evaluation. So let's write it here in green. Ky of f is f of y. Okay, so what I have here is f of tx. Oh yeah, that's exactly the same thing as this, right? So I know that these two things here are related to another, the ones with the wiggles underneath, right? Because this computation was for arbitrary linear functionals f and any point x, right? So in conclusion, I have the following identity. The dual transformation of the dual transformation composed with J is the same as the canonical map composed with T, right? So that will be my helper, because I know this here on the left is compact, right? This is what we already figured out up here before we started this algebraic computation. So this is a compact guy here. All right, and now I claim this identity, this equality tells you immediately that this fella here, that one has to be compact x. Why and why is this? Well, remember this k, besides being a bounded linear transformation, it is also an isometry, right? So it is also an isometry. So in conclusion, let's write down the punchline. And since k y star is an isometry, the above yields at once that not k, that t is compact on x, y. And how do you do this? Well, you go back to the line. This, by the way, would complete the proof of the theorem. You go back to this line. So you have to choose a bounded sequence in the x space, right? And now using this identity there, you can translate it into, well, something bounded in the bidual of x, right? Using the canonical map. That's how it is, right? So if you have a bounded sequence in x space, you just stick it into capital J. J is an isometry, so it maps it to something bounded in the bidual of x. Yeah, but then the bidual of x, that's precisely where the dual transformation of the dual transformation acts on. So you know the image of this guy has a convergent subsequence because you assume the compactness, right, at this moment. And then again, using this identity, you immediately translate this back into a convergent subsequence of the image of T. All right, so do check this for yourself. This is all hidden in this one little identity here. Okay, use the fact that you're playing here around with isometries. The canonical maps are isometries. Okay, good. So having this is indeed the last part of the theorem. This is actually Schauder's theorem. All right, good. Now we have one important corollary of all this, and that's the one for the adjoints. So if you are in a Hilbert space and you have bounded linear transformations from one Hilbert space to another, from one Hilbert space H1 to another H2, then the following statement is true: T is compact if and only if the adjoint is compact. And remember, the adjoint still went the other way, but there's no duals here in the game anymore. Okay, so we have this. This is a corollary. Why is this true? This, by the way, you can prove directly without. What I'm going to do now is I'm going to use Schauder's theorem, what I just proved. But this you can actually prove without any Schauder's theorem, that this is not a hard statement. All right, so How does it go? Well, if T is compact H1, H2, remember how we defined the adjoint? This was an explicit formula. This was T star is equal to C1 minus 1. This was a certain, well, invertible linear transformation, and then a C2, right? That was our formula. So now why does this formula, and together with Schauder's theorem, tell me that the adjoint has to be compact? Well, that's simply because of one of the properties in the last theorem, the ideal character. So if you have something that is compact here in the middle, and you hit it with bounded things from left or right, that's not gonna destroy your compactness of the linear transformation, right? So use the properties 3 and 4 in the last theorem, 3 and 4. And of course Schauder's theorem. You need Schauder's theorem because you need that the green one is compact, right? So that's the important part actually. H1, H2 star and H1 star. Okay, and then this will tell you that this is a compact map from H2 and H1. And how do you do the other direction? Well, you use that fact which the dual transformation does not satisfy, namely if you take the adjoint of the adjoint, then this is T itself, right? So you start with compact adjoint, then you use the first part that you just did, namely that its adjoint is compact, yeah, but the adjoint of the adjoint is T itself, okay? So you're done, all right? So that's much easier. Good. Now, example. So far the only examples that we had were, well, maps on finite dimensional spaces, right? Because there, you know, these images are always compact. Well, the image of the closed unit ball, that's what I want to say. Now here's a non-trivial example, right? So consider integral operators. So this is a guy that we encountered early on in the second week of this class, though the example is still in the first sort of section before the Hilbert space stuff starts. So this is our integral operator, kfx, which has a kernel, small k, in two variables, fy dy, and the kernel here is a function in two variables which is continuous on that square. So in R2, 0, 1 cross 0, 1, right, is continuous on the square 0, 1 cross 0, 1, which is compact, and that plays a role because if you have continuous functions on compact sets, then those guys are uniformly continuous. So your deltas do not depend on the points that you use in the continuity module. All right, we know, and this we already figured out when we discussed this example, so we convinced ourselves that this is a bounded linear operator, and to figure this out we had this little estimate. This is just the triangle inequality for the integral. You go inside, you optimize the kernel, you have this, and then what's left is the f of y that you also optimize. That's why you have the infinity norm out there, and then you have an integral from 0 to 1 over a constant which is equal to 1. Okay, that's why we have this. So now I'm going to use this to show that this is a compact operator. And for this I again need Arzela-Ascoli. So for an arbitrary bounded sequence Fn, so that's a sequence of continuous functions, and any x prime, say, in 0, 1. So I have to show that, well, this defines a family of uniformly bounded equicontinuous functions on 0, 1. All right, so let's do this. So the image sequence, that is, right? Because I have to select a convergent subsequence from the image, not from F, from the Fn sequence, right? So I have to look at the image, kfn x minus kfn x prime, say. All right, so first, okay, so what happens here is, well, so let's write this out. So we'll have the kernel kxy, and then we will have kx prime y, because it's linear, right? Taking an integral is a linear operation, and then you have this. So now you do the standard trickery again. You go inside with the absolute value, you optimize the fy part. Actually, there's an n, the subscript n, right? Because these are fn's, f sub n of y. So you optimize those, you get the infinity norm out, and then inside you have, at this point, kxy minus kx prime y, something which does not depend anymore on small n, the member of your family, the index that your members run through. All right, but now, how do I control that last piece? Well, this is because I have uniform continuity, but k is the kernel, is continuous on 0, 1 cross 0, 1, so uniformly continuous. Uniformly continuous, meaning for any epsilon positive, we can find, that's what I said earlier, that delta only depends on this epsilon, not on the point that you are zooming in. So that kxy minus kx prime y less than for delta whenever x and x prime are sufficiently close for all, that's the punchline here, for all y in 0, 1. Okay, hence whenever x minus x prime is sufficiently close, we have the following estimate of k fn x minus k fn x prime. We just continue from up here, because now you have control over that integral. So that will be less than epsilon in the integrand, and then the length is 1, so you just have epsilon fn in infinity norm, right? This shows this estimate, the last one, this shows that the following family, so that is the image sequence, this is a family of continuous functions defined on a compact interval on the real line, is a family of, well, equicontinuous. This is precisely this fella here. That's where it comes from. And the uniformly boundedness, that we already know, right? So it's a family of equicontinuous, uniformly bounded. Where's the first one here? Maybe in red, right? Because my sequence is bounded, so if you index this here with small n, then this guy here on the front is certainly bounded, because I choose this bounded sequence, right? So the uniformly boundedness comes from the red part. Okay, it's uniformly bounded. Family of this uniformly bounded continuous. Well, that uses calculus, right? So if you take this, that's why your kernel has to be continuous, because you take a continuous function, you integrate it against something continuous, and then the result as a function of x is again continuous. But this we discussed when we first discussed the operator. Equicontinuous uniformly bounded continuous functions. Thus, Bayer-Sela Ascoli again. Ascoli. There exists a, uniformly convergent. Okay, this I don't need that word here. is a convergent subsequence. It is uniformly convergent if you evaluate it on the x, but that's not what I'm writing. Is a convergent subsequence k, f and k, k1 infinity in f. All right, and this shows that the integral operator is compact on my space X. Okay, good. That's the very first important very important example of a compact operator. These are the integral operators on continuous functions. Now, but this is of course hard to prove because you need a heavy theorem. Without Ascoli, there's on that space of continuous functions, there's, you know, without it, there you will be lost. There are other function spaces on which you can make sense of integral operators. These are Lebesgue spaces. There it's much easier to show something like this, but again, we are not discussing, or we're not using measure and integration theory in our complex analysis module. So I have to discuss this one with the continuous function. So I have to use Ascoli. Now, let's discuss another property of compact operators. If you have something compact linear transformation between two Banach spaces, x and y, then T maps weakly convergent. So remember this stuff, weakly convergent sequences. It maps weakly convergent sequences into norm convergent ones. Okay, so that is a nice property, right? Into norm convergent ones. Okay, so proof. Well, let T be compact. And then after we've had this theorem, I will discuss if this is a two-way road. And in general, it's not. Okay. And if you take a sequence in X with weak limit, so remember weak convergence was this half arrow, so xn to x as n tends to infinity. Now what I have to do is I have to look at the image sequence and show that this converges in norm on y, well, to something. Okay. Probably have an idea what something is, but first and observe that for any, well, linear functional on y star, so we have fyn minus f t of x. Now, yeah, okay, this is because these are linear things, so yn minus t of x, and now you use the dual transformation. The dual transformation tells me that because yn is t of xn, so this is the dual of t acting on f evaluated on the difference xn minus x. Okay, that's what I get from the dual. Okay, but now look, what does the dual do? So the dual is a map from the dual space of y to the dual space of x. So in other words, this guy here, this bracket, this is a linear functional on x, right? But my sequence is weakly convergent. So that means as n tends to infinity, this guy goes to 0, right? And since this holds for any linear functional on f, this just shows that this sequence yn converges weakly to t of x. And that's what we're going to call y, okay? As n tends to infinity. And this is an element in y. Because t maps capital X to y. Right? As n tends to infinity. Okay, so what I did right now is I haven't used the compactness at all at this moment. I've just shown that a weakly convergent sequence is mapped here to a, well, weakly convergent image sequence. Right? So that maybe not so surprising. Now what we do is, and that uses compactness, now suppose that sequence yn does not converge in norm. Does not converge to y in norm. Okay, So that means there exists epsilon positive and a subsequence ynk yn, subsequence of yn, so that, these guys stay away from the y. So the distance between y and k and y in y space is bigger than epsilon for all members, for all k, right? But ynk, which is tx and k, and x and k is of course bounded. Is bounded. Good. So thus, by compactness, now we use it, thus by compactness of T, there exists convergent subsequence. There exists a subsequence YNKM, which is a subsequence of the YNK, such that the YNKM, well, they converge in norm to some element y hat, but this y hat of course has to be different from the y above, because I assumed that my sequence yn does not converge in norm to y, so in particular none of its subsequences will converge to y, right? So whatever this limit is there with the hat, it's going to be different from y by assumption. Okay, good. Right. So now time-wise we're kind of off. So maybe I will stop here and not go over time again. So we have to still complete the argument here, but there's not much left. We are almost there. We almost have the contradiction. Once we have the contradiction, then this contradiction comes because weak limits are unique, right? So that's the thing. Because this sequence here, maybe I'll say it in words and write it like next time. So this sequence, the subsequence YNKM that converges in norm to y hat, of course it also converges weakly to y hat, right? But YNKM is a subsequence of yn, and we already know yn converges weakly to y. So in turn, this YNKM has to converge weakly to y, and that's your contradiction. Good, but once I will write this down next time, and then I will make a quick remark about whether this is a two-way street, or to say if you have a bound linear map that maps weakly convergent sequences to norm convergent ones, can you always conclude that that thing has to be a compact linear transformation? I will clarify this next time. Once we're done with this, then we will build more theory, and we are gradually then approaching the big spectral theorems. Okay, I'll see you next time.